All right, everyone. I've selected a few problems from our Unit 1 review, as you can tell from the title of the video. I just want to pick a few and work through them. I know there were some questions on this particular problem, so we're going to look at numbers 3, 5, and 17. So here on number 3, we are asked to graph and identify the transformations of this function here, f of x, equals the absolute value of 2x minus 1. The way we want to approach this is basically we need to deal with the fact that there is both a horizontal shift and a horizontal compression. And when we talked about transformations in our notes, we talked about how we always want to apply them in the order of operation. So if we were to do that, there's really two different ways that we can approach it. Basically, anything in black you see would be if we were to just treat 2x minus 1 as the argument through the order of operations, the 2 here would have to be dealt with first. That would create our horizontal compression by 1/2. And then this rightward shift by 1 would also need to be accounted for. But because the entire graph has been compressed by a factor of 1/2, this 1 here, if I'm using air quotes, I know you guys can't see me, that 1 there is also subject to that same compression. So instead of moving over a full unit, we'd also have to compress down the horizontal shift itself. So we would actually end up shifting right a half of a unit. That can be tricky. So what I have done in the past is kind of forced the order of operations through factoring. So if I factor that leading coefficient of 2 out, I can basically achieve the exact same, a different form of the exact same function. Okay, so pulling that 2 out, well, now we have that forced order, and maybe this makes a little bit more sense as far as what's really going on from a transformation perspective. But we are now, because we have a forced order through factoring, we're going to deal with what's in the parentheses first. So that would cause our graph to move right a half of a unit. And then the 2 on the outside, this 2, on the outside of the parentheses, but still inside the absolute value, well, that 2 would cause a horizontal compression by 1/2. So either way we go, we have these same 2 transformations. I know a lot of us have been using the tables to transform, right? So just so it's clear, I tried to get this all in one table. So we are going to transform our parent function one of 2 ways. Either we need to add 1 and then divide everything by 2, as you see here in black, or we can take our x value, cut it in half, and then add 1/2, as you see here. In either case, the x coordinates end up the same. You can see we have those 5 coordinates of negative 1/2, 2, 0, 1, 1/2, 0, 1, 1, and 3/2, 2 in both cases. So what that would look like, it would look something like this. There's our vertex at the point 1/2, 0. And then we're going to move out half of a unit in each direction, and each half unit move will account for a 1 unit increase in the vertical direction. What do I mean by that? Well, there's a point, and there's another couple points. Those 5 are what we have on our table, so we will sketch that through those 5 points. Let's look at another problem, number 5, right below number 3. I went ahead and started just by setting up my table, my parent function, and I set up my grid here, knowing that the shape of this square root function looks something like this. I know with no negative signs, I should really only exist in my first quadrant. So what's going on here from a transformations perspective? Well, there are 2 multipliers, right? There's a 1/3 multiplier inside and a 2 outside. So that 1/3 inside the operation, Remember, whenever we're multiplying inside a square root or a quantity being squared, we need to take the reciprocal. So this 1/3 is really going to be a horizontal stretch by the reciprocal of 1/3, or just 3. Then our 2 on the outside is going to account for a vertical stretch by a factor of 2. When we're outside the operation, we can just multiply. What values will this affect? Well, the horizontal stretch will affect our x values, and a vertical stretch our y. The way we are going to set up our table, our x values should become 3 times as large if they are going to horizontally stretch. Oh, sorry, I have the wrong color coding there. And then our vertical stretch is accounted for by making our y values larger. So from here, I'm really just plugging in and transforming the 5 points from my parent function. So 0, 0 is on my transformed function, the point 3, 2. And you can see I changed my scale a little bit just to account for these points. 3, 2 would be right there. We have the point 12, 4 on our graph. And I don't think 27, 6 will quite fit, but 12, 4 will be our last point. So our graph will take that familiar shape. But with our table of values and our scale, we can see that it is not just our parent function, it has been scaled up. Just one more problem we were going to look at in this particular video, and it is number 17. And what we're looking for on this particular problem is the domain. So what possible issues could come up here? Well, I have a square root in my numerator. So whatever goes into my square root, 2 plus x squared, must be greater than or equal to 0. And then I also have a denominator. So whatever this whole quantity ends up being cannot, cannot equal 0. So I'm going to solve each of these inequalities / non-equations to figure out my domain. On the left-hand side here, I can subtract 2. And I have x squared is greater than or equal to negative 2. Well, here's where I can kind of pause. X squared is always 0 or positive, so it is always true. Our domain for this particular part would go from negative infinity to positive infinity. Why is that the case? Anything squared cannot be negative. So no matter what we plug in for x, we will always get a quantity that is greater than negative 2. Well, now we want to figure out the other part of our domain. Well, I can cube both sides, so I'll have 2 minus x does not equal 0. I can add x to both sides. So as long as x does not equal 2, my function is defined. So to write this domain in, I'll do it in both forms. In interval, our only disallowed value is positive 2. So we would go from negative infinity to 2 in union with 2 to infinity. For set builder, we're really going to say the same thing for our domain. It's going to be all the x values such that x does not equal 2. There we see 2 different ways to describe our domain in interval and set builder. Remember, when we focus on domain, we want to find values that break the domain. Things like zeros in the denominator and square or any even root that has a negative argument inside. Thanks, everybody.